This is Y. Manohar Reddy, Assistant Professor, Department of Cybersecurity, Institute of Aeronautical Engineering. So today I am going to discuss about the next theorem, Fermat's theorem. So we already discussed about the Fermat numbers, Mersenne prime numbers, and different types of prime numbers in the previous sessions. Today we are going to discuss the Fermat theorems. So basically Fermat theorems states that it is very important for modular numbers, and it is used to find the Euler quotient function values also. So we'll go with the Fermat's theorem right now. So how we are looking here. So Fermat theorem. So Fermat theorem is also known as Fermat's little theorem as well as Fermat's primarily test. So Fermat's theorem is also known as Fermat's little theorem and Fermat's primarily test. So because it is going to test each and every natural number as well as each and every prime numbers to find the different types of Euler quotient function values. So that's why we are going to say that Fermat's primarily test. So Fermat's primarily test or Fermat's little theorem. So this is the way we can say that it is a little theorem or primarily test. And any prime number p and any integer a. So any prime number p and any integer a. So you can take any of the integer positive value and any of the prime number p. So such that p does not divided a. So p does not divided a. That means p, suppose p equals to prime number 3 you can take, and a integer 2 you can take it. So p does not divide a. The pair are relatively prime. As we know that 2, 3 are pairwisely relatively prime. You know that already, right? So as well as p divides exactly into a power p minus a. So it divides exactly into a power p minus a. So suppose you can take p as a prime number called 2 and a as a, you can take any of the integer 4. So then a power p minus a, 4 power 2 minus 4, that is nothing but 16 minus 4, that is nothing but 12. 12 is divides with the p value. So p value is what? 2. So exactly this p equals to 2 is going to be divides 12. So that is why you can say that p divides exactly into a power p minus a. And similarly you can take another one. So like p equals to, and prime number 3 you can take, and a equals to, you can take any of the integer 2. So 2 power 3 minus a, 2 power 3 minus a is nothing but 2. So 8 minus 2 equals to 6. So 6 is divisible by p prime number. So you can say that p divides exactly into a power p minus a. Right. So although a number n that does not divide exactly into a power n minus a. So in this a power n minus a case, that divides, n does not divides exactly with the a number, and a power p minus a in this form, the p is divided to the a power p minus a value. So it must be a composite number, and the converse is not necessarily true. So this condition is not going to be true because it is not divides with the n number, but it becomes true. This becomes true because a power p minus a divides p exactly. So the Fermat's theorem tests that it is a primarily test with the help of integers comma prime numbers. So when it divides a power p minus a, it is true, and a power n minus a, it does not divide, so it is not necessarily true. So that's why you can say that Fermat's theorem is going to be performed on these prime numbers and any of the integers, right? So like the way you can understand this theorem supports to this formula a power p minus a, and it does not supports to a power n minus a. So here n is nothing but any of the integer you can take n equals to natural integer, right? So now coming to the theorem proof. So theorem proof you will see here. So here the theorem a power p minus 1 congruence to 1 mod of p. So we already said that this is a congruent symbol. If you are not able to pronounce it, you can pronounce some simple like equal. So equal, you can say that. So the theorem says if p is a prime and a is a positive integer with p does not divides a. We already discussed in the previous sessions. If any of the number a comma n, if it divides, then you can say that a by n. If those two does not divides, then you can write a not n. This is we've already discussed in previous sessions, right? So here we are going to state like that only. So if p is a prime and a is a prime or positive integer with p does not divides a, then you can say that a power p minus 1 congruents to 1 mod of p. A power p minus 1 congruents to 1 mod of p. So you need to satisfy this. And you can also remind that this theorem states that a power p, show that a power p minus 2 is the inverse of a modulo p. So a power p minus 2 is the inverse of a modulo p. A modulo p. So a modulo p is the is for inverse of a power p minus 2 value, and a power p minus 1 mod of p. So you can see and you can state them both. Right, now we now present a couple of theorems that are direct consequences of Fermat's theorem. So to sequence we are going to state that the first states Fermat's theorem in a different way. It says that the remainder of a power p, that says that remainder of a power p when divided by p, as soon as we discussed, right? So here the previous a power p minus a we divides, right? So that is what we discussed here. So a power p when divided by p is the same as the remainder of a when divided by p. So the same remainder will come when a when divided by p. The other theorem determines the inverse of an integer a modulo p. So one is straightforward number and second one is the inverse of that integer a modulo p. So where p does not divide a, this is what we mentioned here. P does not divide a, right? So we have to state the two forms. One is the a power p when divided by the p is the same as the remainder of a when it divides p. And the other theorem states that the inverse of an integer a modulo p where p does not divide c, right? So like these two ways you are going to state this theorem, right? Okay, fine. Then next, if p is a prime number and a is a positive integer, then you can write a power p congruents to a mod of p. A power p congruents to a mod of p. Definitely you can write this from this formula. A power p minus 1 congruents to 1 mod of p. From these, you can write a power p equals to simply. So a power p minus 1 equals to 1 mod of p. You can write a power p minus, you can write like a power p by a equals to 1 mod of p. So that is you can write like a power p equals to a mod of p. A mod p. So like the way you can write, this is what we get here, right? So similarly, if p does not divide a, if p does not divide a, by Fermat theorem we know that a power p minus 1 congruents to 1 mod p. That is what we started, we stated here from starting point. We stated here, right? So thus we get a power p equals to a mod p. This is what here, right? So not now if p divides a, we have a power p equals to a power a equals to 0 mod p. We have to assume this. A power p equals to a equals to 0 of mod p, because that a power p when divided by p is the same as the remainder of a. That same as the remainder is 0. So that is what we mentioned here from this statement, right? So this is what we mentioned from this statement. So if p is a prime number, if p is a prime number and a is an integer such that p does not divide a, then a power p minus 2, a power p minus 2 is the inverse of modulo p. A power p is the inverse of a modulo p, right? So this is what we have to see here. And if p does not divide a, then Fermat theorem says that what? A power p minus 1 congruent to 1 mod of p from first one, right? Hence substitute this one, a power p minus 1 into a power 0, a power 0 or a power 1, that equals to 1 mod of p. So this is we are getting from these statements, a power p minus 1 equals to 1 mod of p. So if divides with a, then you can write a power p minus 1 by a equals to 1 mod of p, 1 mod p. So that you can write like a power p minus 2 equals to 1 mod p, 1 mod p. So this is the way you can write a power p minus 2 equals to 1 mod of p from this statement, right? So as a result, we can say that a power p minus 2 is the inverse a modulo p, is the inverse a modulo p. So if you can send this one from this, if you can send this one to this side, a power p minus 2 equals to, you can write what, a inverse of modulo p. This is what you can write, right? So that's why we are stating here a power p minus 2 is the inverse of a modulo p. So like the way you have to state this theorem. So one thing you have to remember this one. So a power p is the value and p is the prime number. If both divides, then you can write p divides a, or if those two does not divide, then you can write p does not divides a. So as per the basic principle, we are going to state and prove this theorem as like a power p minus 2 is the inverse a modulo p. So this is the way you can describe and state this theorem. Okay, fine. So the next one is we are going to find the Euler torsion function and Euler's theorem. Euler's torsion function and Euler's theorem. So Euler's torsion function. So Euler's torsion function, simply you can say the symbol, that is nothing but symbol pi, right? Or pi is a function, is a very important number, that theoretic function having a deep relationship to the prime numbers and the so-called order of integers. So if this pi of n is going to say that it is a Euler torsion function and it relates with the prime numbers, and order of an integers. So you can say that this pi of n is going to have a deep relationship with the prime numbers as well as order of integers, right? So the torsion function pi of n of a positive integer n greater than 1 is to be defined of the number of positive integers less than n that are coprime. So here we are going to say that if n greater than 1, it is a positive numbers, it is defined as the number of positive integers. If it is less than n that are co-prime to the n, we are going to say that, right? So if suppose if pi of 1 is defined as to be 1, pi of 1 is defined as the 1 simply. So here we are going to say that pi of n equals to, you can write any of the number n or 1 or something. So if you find pi of n, so automatically the n value is 1, so pi of 1 equals to 1. So that is what we defined here. So this phi of n Euler torsion function is going to have the deep relationship with the positive integers, deep relationship with the prime numbers. That is what we mentioned here. So simply Euler torsion function is used to find the different values with the help of the deep relationship with the prime numbers and the order of an integers. So it represents pi of n, and we are going to find the different values. We'll see how that values are coming here. So see here, the following some n values and pi of n values here. The following some n values and pi of n values. So this is the n value. This is the n value, and the pi of n equals to pi of n. So n equals to 1, then pi of n equals to, so pi of 1 that equals to 1 as it is, right? And the next n equals to 2, n equals to 2, so pi of n equals to 2. So you can write pi of 2 that equals to n minus 1, that equals to 2 minus 1, that equals to 1. The value will get here. Numbers co-prime to n, here you can find the formula with the help of pi of n equals to n minus 1. So with this formula only, you can find these co-primes. You are going to find the co-primes with the help of this Euler torsion function phi of n, right? So suppose you can take this n equals to 3, then pi of n equals to n minus 1, that is nothing but pi of 3 equals to 3 minus 1, that equals to 2. So the pi of n value is 2 and the number of co-primes are 1 comma 2. For the prime numbers like 2, 3, 5, 7, this 11, for these all the prime numbers, the co-primes are up to previous number, that is, for example, you will take 11, the previous number is what, 10, up to the 10, all the numbers are co-primes to this number, you can say, right? All the previous numbers up to 10, you can say that co-primes to this number. Similarly, you can see here 7. For this 7, the last previous numbers are 6 up to 6. These are all the co-primes to this 7, you can see. And similarly, pi of 5. So 1, 2, 3, 4 last sequence, up to last sequence, the values are 4 is to be the co-primes to this 5. And for the 3, so like the way you can find all these numbers. So for this is all for prime numbers, but for the composite numbers, so here the 4 is one composite number. Why we are saying this 4 is a composite number? It is a greater than 1, the number is greater than 1, as well as the number is not prime, right? The number is not prime. So that's why you'll see here it is a composite number. But for the composite number, we are going to find like what? Pi of n equals to a into b or m into n. The way you have to define like this. Suppose pi of n equals to what? 4. Pi of n equals to 4. But for pi of n equals to 4, but pi of n you can write like 4, 2 into 2, right? So pi of 2 into pi of 2, you can write. So pi of 2 is what? 1. And pi of 2 is what? 1. 1 into 1, 1. 1 you have to get. But here the 2 is came here. For these composite numbers, we can have another formula, that is we'll discuss in the next slide. Okay. So that pi of 4 and pi of 6. So pi of 6 and these composite numbers. For all these composite numbers, some of these composite numbers we are going to see in the next slide, all the formulas. Okay. So remaining all these pi of 9 values, pi of 10 values, these are all some composite numbers we are going to see like this way. So for the prime numbers only, you can see the last sequence of the numbers are co-primes to the prime number. But for composite number, some of the composite numbers having this formula, pi of n equals to a into b or pi of m into pi of n. You can follow this formula, or else some of them are having a different formula that we will discuss in the next slide, right? Okay. So this is the way you can see all the pi of 3, pi of 13 values also same here up to 12. So you just have the just have the same thing. All the prime numbers, for all the prime numbers, the co-primes are up to the last sequence of that number. So that has to be defined. Okay, right? So for the pi of 15 also, you can write pi of 3 into pi of 5. Pi of 3 into pi of 5. So pi of 3 is what? 2, and pi of 5 is what? 4. So pi of 15 equals to 2 into 4, that equals to 8. So 2 into 4 equals to 8. So this is the what you have to mention here. Okay, this is what you mentioned here. Okay. So up to this, all of you clear? Right. And next here we'll see some different values. We will see some different values of Euler's torsion function. So n equals to 1, then pi of n equals to 1 automatically. If n equals to 2, then pi of n equals to 2 minus 1, that is nothing but pi of 2 minus 1, 1. And 3, for the 3 value, pi of n equals to n minus 1, 3 minus 1, that equals to 2. So these are all the different values. For the n equals to 4, pi of n equals to 2. And for the n equals to 5, pi of n equals to 4. N equals to 6, pi of n equals to 2. N equals to 7, pi of n equals to 6. And n equals to 8, pi of n equals to 4. N equals to 9, pi of n equals to 6. So this is the way you can see all the different types of n values and pi of n torsion function values. So these are all co-primes to this all the n integers. So n is a normal, n is a natural integer, n is a natural integer, and pi of n is the Euler torsion function values, or you can say that co-primes values. Euler torsion function values, Euler torsion function values, or you can say that co-primes of the n values, co-primes of the n values. You can say any way. So co-primes of the n values, or you can say that Euler torsion function values. So this is all some up to 31. Up to 30 you can see all the different types. So from this table you can observe one thing. We have observed one thing for all the prime numbers. 2, 3, 5, 7, and 11, and 13, and 17, and 19. You can observe this all. 23, so 20, 29. So you can see all these different types of prime numbers. For this all the prime numbers, we already said that the co-primes are up to the last sequence, So that means from 7 for the 17, last sequence is what? 16. So up to last sequence, these are all the co-primes to this natural number. Similarly, for the 13, the last sequence of the numbers 22. For the 29 also, the last sequence of the number 28. Similarly 11. Similarly 13. So you have to observe this carefully, because for the co-primes, for the prime numbers, for the prime integers, you can say that all the last sequence of the number is to be the co-primes to the natural number. So this is the way you can find some Euler torsion function values, or you can say that co-primes to this natural integer values, right? So this is the way you can find this all the values. And here we already know that one thing. So for the composite numbers, how we are going to find that? For the composite numbers, so suppose n equals to 4, so pi of n equals to pi of 4. We already said that pi of 2 into pi of 2. So actually we have to got the result. Pi of 2 value is what? 1. Pi of 2 is what? 1. So 1 into 1, 1. But as per this value, pi of 4 equals to 2. So how we got this one? So for the composite numbers, we have a separate formula. So we will see. So here we found some relationship between n and pi of n. So one thing you may have noticed is that what? So when n is a prime number, example 2, 3, 5, these are all. So the value is what? Pi of n equals to n minus 1. That is what you followed here. Okay. Then, but for composite numbers, what? But composite numbers, we noticed that. So that is what, for example, 15 equals to 3 into 5. 3 into 5. So pi of 15 equals to pi of 3 into pi of 5 you can write. So pi of 3 is what? 2 actually. Pi of 5 is what? 4. So pi of 15 equals to 2 into 4 equals to 18. 8. Right? So that is what good. So this is also true for 14, 12, 10 and 6. So for this some values, this formula is correct. This formula is true. However, it does not hold for 4, 8 and 9. But it does not true for these 4, 8, 9 values. Why we need to show? We need to see why it is not holding for true, right? So for example, here 9 equals to what? 3 into 3. But pi of 9 equals to 6. But pi of 9 equals to 6 value. So that is not equals to pi of 3 into pi of 3. So pi of 3 is what? 2. Pi of 3 is what? 2. So 2 into 2, 4. In fact, this multiplicative relationship is conditional. This multiplication relationship is conditional. So as per this formula, as per this scenario, we are saying that for these 14, 12, 10 and 6 values, this pi of 3 into pi of 5, this value is true. This value is true. But for this 4, 8, 9, this formula, this form is not true. So we'll see how this will be calculated. So So when m and n are co-prime, when m and n are co-primes, so then pi of m into pi of n equals to pi of m into pi of n. This is what we mentioned here in the previous slide. Previous slide we mentioned here. The general formula to compute pi of n is the following. So if the prime factorization of n is, we already said that prime factorization. So p1 power a1, p2 power a2, like the way you can see the different types of prime factors. So here also you can see here n equals to p1 into e1, p1 power e1 and p2 power e2, like the way you can see p1 power e1, p2 power e2, p3 power e3. So up to pn, en. This is the prime factorization form. And for the pi of n equals to, is this formula is especially for this what we 9, 4, 8. Those the values who does not have hold for the true from the composite number formula. The values those who does not hold the true for this for this composite number formula, they can follow this formula. That numbers follow this formula. So what is that formula? So pi of n equals to n into 1 minus 1 by p1 into 1 minus 1 by p2 into up to 1 minus 1 by pn, 1 minus 1 by pn. Up to this we have to find out, right? So we will see. So for these values the formula, composite number formula, is not holding true. So that's why we are going to find these values with the help of this formula, right? So this is one formula to holding these values to be true. So example is what here. So 9 equals to 3 square. 9 equals to 3 square. So 9 equals to 3 square you can write, and pi of 9 equals to 9 into, so where here n equals to 9, so you can write pi of 9 equals to n into, so that n means 9 into 1 minus 1 by p1. P1 is nothing but 9, you can write 3 square, right? So this is the p1 value and 2 is the e1 value. So here p1 equals to what? 3 and e1 equals to what? 2. So these are the values. So substitute in this formula n into 1 minus 1 by p1, because we writing only 3 square is enough for 9, so that's why. So p1 you can write like 9 into 1 minus 1 by p1 is nothing but 3. So 9 into 1 minus 1 by 3, that equals to 9 into 1 minus 1 by 3 is nothing but 2 by 3, and 3 1 ja 3 3 ja, so 3 into 2 6. So pi of 9 equals to 6 is holding true. Pi of 9 equals to 6 is holding for true. So this is the way you can substitute in the formula. Similarly, you can take the next value is what? N equals to 4. So see here, n equals to 4. So pi of n equals to what? The formula n into 1 minus 1 by p1. Right. So here 4 is nothing but you can write like 4 equals 2 square. So the p1 equals to 2 and the e1 is also 2, right? So substitute these two values in the formula. So n equals to what? 4 into 1 minus 1 by p1 is what? P1 is also 2. So write 4 into 1 minus 1 by 2 is nothing but 1 by 2 you can write. 1 by 2 you can write. So 2 1 ja, 2 2 ja. So 2 into 1 is nothing but 2. So pi of 4 equals to 2. The value will get. But for the Euler torsion function value, actually pi of 4 equal to, you can write like pi of 2 into pi of 2. So pi of 2 value is 1, pi of 2 is value 1, 1 into 1, 1. But from this formula, you are going to get pi of n equals to, that means pi of 4 equals to 2, right? So that is right? So again, you can see here 8. Again, you can see here 8. So 8 you can write like what? 8 equals to 2 power 3. 2 power 3. So here P1 value is what? 2 and E1 is value as 3. So substituting these values into the formula. So pi of n equals to pi of 8 equals to n n into, that means 8 into 1 minus 1 by p1. 1 by p1 is nothing but what? 2. So 8 into 1 minus 1 by 2 is nothing but, you can write 1 by 2. So 2 1 ja, 2 4 ja. So 4 into 1, 4. So pi of 8 equals to 4. So pi of 9 equals to 6. Pi of 4 equals to 12. Pi of 8 equals to 4. And also you can say that 15, for the 15, pi of 15 equals to. So pi of 15 equals to, you can write like what? Pi of 5 into pi of 3, right? Pi of 3. But see here, n equals to 15. And you can write like what? 3 power 1, 5 power 1. So you can substitute them into this formula. So n into 1 minus 1 by p1. So here p1, p2, you can have these two values. This is p1 and this is p2. So substituting those p1, p2 values in this formula. So n equals to what? 15 into 1 minus 1 by p1 is what? 1 by 3 into 1 minus 1 by p2 is what? 5. P2 is what? 5. So 15 into 1 minus 1 by 3 is nothing but 2 by 3, you can write directly, into 1 minus 1 by 5 is nothing but 4 by 5, you can write directly, 4 by 5. So 3 5s and 5 1s. So directly you can write 2 into 4, directly you can write 2 into 4, that equals to 8. So pi of 15 equals to 8. Pi of 15 equals to 8 value you should get here. So this is the way for the, you can write the different types of composite numbers substituting in this formula. So here we got it what? Pi of 15, pi of 8, pi of 9 and pi of 4 is, by substituting in this formula we got the correct result, and those values are holding true values. Those values are holding true values, right? So this is the way you can say that. So this is the scenario. You can find these all the composite numbers Euler torsion function values. So find out the Euler torsion function values using composite numbers here, right? So this is the way you can see. And here the next one is Euler's theorem generalized that the Fermat's theorem to the case where the modulus is not prime. So where the modulus are not prime, then how you are going to find this? So see here, if n is a positive integer, and a comma n are co-prime, then you can write the formula is what? A power pi of n equals to 1 mod of n. A power pi of n equals to, that is nothing but congruence to. We have to pronounce like congruence to. If you are not able to pronounce it, you can pronounce like equals. So a power pi of n equals to 1 mod of n, where pi of n is the Euler's torsion function. Where pi of n is the Euler's torsion function. So where n is the natural number and a is the co-prime number. So you can take this example. So a power pi of n equals to 1 mod of n. You have to satisfy this condition. For this a comma pi of n are the co-primes are prime integers. If you want to say that a comma pi of n are the co-primes are prime integers, you should satisfy those two into this formula. So a power pi of n congruence to 1 mod of n. Suppose you can see here, if a equals to 3 and n equals to 10, so substitute them into this formula. So a equals to a power pi of n equals to 1 mod of n, 1 mod n. So a is what? 3 power n is what? Pi of 10. So pi of 10, that congruence to 1 mod of 10. So a power pi of 10. So we need to see from the table pi of 10. What is the value of pi of 10 actually? You can write like pi of 5. You can write like pi of 5 into pi of 2, right? So pi of 5 into pi of 2. So pi of 5 is nothing but 4 into pi of 2 is nothing but 1. So that is equal 4 into 1, 4. 4 into 1, 4. So you can write pi of 10 value 4. So directly you can substitute 3 power 4 congruence to 1 mod 10. 1 mod 10. So substituting this here, and 3 power 4 value is what? So 3 into 3 into 3 into 3. That is nothing but 3 3s are 9, 9 3s are 27, 27 3s are 81. So 81 congruent to 1 mod 10. 1 mod 10. That means if you are dividing 81 with the 10 value, definitely you should get the remainder is 1. Yes, so that's why it's satisfied. That's why it's satisfied. So 81 equals to, so see here, 10 of 81, 10 of 81, 10 is a 80. So 1 is the remainder. So 1 is the remainder. So 1 mod of 10. So you can say that 1 mod of 10 correctly. 1 mod of 10 correctly. So from this formula you can say 81 equals to 1 mod 10. So that is nothing but a power pi of n congruent to 1 mod n is satisfied for this values, a equals to 3 and n equals to 10 values, right? Similarly, you can see another example, a equals to 2 and n equals to 11. So a equals to 2 and n equals to 11. So what is the values we will get here? So a equals to 2 is what? So 2 power pi of n. N equals to what? So 2 power pi of n congruent to 1 mod n. 1 mod n. So a nothing but 2 and pi of n is nothing but pi of 11. So pi of 11 congruent to 1 mod n. So here pi of n is what? 11. So pi of 11 equals to n minus 1, that equals to 10. So you can write pi of n. 10 is instead of writing pi of n. So 2 power 10 equals to 2 power n congruent to 1 mod n equals to what? 11. 1 mod 11. So if it satisfies, then you can say that it is satisfied. So see here 2 power 10 is what? So you can write 2 into 2 into 2 into up to 2 power 10 times. So the value is what? 1024. 1024. So you can divide this 1024 with the help of 11. So what will you get the result? See here. So 11 9s are 99 and the 3 is here and 4 here. 11 3s are 33. So the remainder is 1. So you can say that 2 power 10 congruent to 1 mod 11. So this is the, you can see all the different values. So that's why you can say that for these prime integers, for these co-primes, the formula is from Fermat's theorem. Definitely it's satisfied. Definitely it's satisfied. So these are the values. Suppose you can take another values like a equals to 4, a equals to 4 and n equals to 3 you can take. And suppose you can see here a equals to 4, n equals to 3, whether it is satisfied or not. See here. So a equals to 4 and n equals to 3. So n equals to 3, then pi of n equals to pi of 3. So pi of 3 is nothing but pi of 3 is nothing but 2, right? So a equals to what? 4. So 4 power 2 congruent to 1 mod 3. See here whether it is satisfied or not. 4 square is nothing but 16. 16 congruent to 1 mod 3. See, let divide here. So 3 is here and 16 is here. 3 5 is 15 and the remainder is 1. So 16 congruent to 1 mod of 3. 1 mod of 3. So definitely it's satisfied. Where a equals to 4 and n equals to 3 value. A equals to 4 and n equals to 3 value. It's satisfied definitely. Similarly, you can take another value like a equals to, suppose a equals to 5, n equals to same, n equals to 3, you can take a equals to 5 and n equals to 3. So substitute them, a power pi of n. So a is what? 5 power pi of n is what? Pi of n equals to n minus 1, that is nothing but 3 minus 1, that is nothing but 2. So 5 square congruent to 1 mod 3. 1 mod 3. See here whether it's satisfied or not. 5 power 2 congruent to 1 mod 3. So 5 square is nothing but 25. 5 square is nothing but 25 and mod 3. So 3 is here. So if you divide 25 with the 3, so 3 is a 24 and 1 is the remainder. So it's satisfied. So that's why we are saying that if n is a positive integer and a comma n are co-primes, A comma n are co-primes, definitely they must be satisfied this formula. They must satisfy this formula with the help of this pi of n torsion function values. Pi of n torsion function values. So this is the way you can understand to find the pi of n values and satisfying this formula with the help of a comma n positive integers or a comma n co-prime integers also, you can say that, right? So this is the way you can say all these formations. Okay, so that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.